Well, hello again. We are moving on to the next chapter in discrete mathematics, which is proofs and recurrence relations. We're going to talk about two types of proofs today, and the first of those is proof by contradiction. And let me just show you how that works, and then we'll go through an example of that. You can prove that a statement is true by showing that if the opposite was true, it would contradict some of your assumptions or something that we already know to be true. Okay, so that's basically what we're going to do. Rather than prove something to be true, we're going to try and show that the opposite is true and then come across some kind of contradiction, which means that the opposite can't be true. So for example, we're going to prove that the log base 2 of 5 is an irrational number. And we're going to do that by contradiction. So we assume that the opposite is true. We assume that it is actually rational. And hopefully we'll come across some kind of contradiction to this. If the log base 2 of 5 is actually rational, then it can be written as p over q, where p and q are integers, and they have no common factors, and q is not equal to 0. Okay? Otherwise, it would not be rational. So that means that we are going to assume that log base 2 of 5 can be written in that way. Well, if that's true, if the log base 2 of 5 is equal to that fraction p over q, then I can rearrange that in exponential form to say that 2 to the power of p over q is then equal to 5. That's just a simple rearrangement of what I assumed. And so if I raise both sides of that equation to the exponent q, then the left side becomes 2 to the p and the right side becomes 5 to the q. Well, there's only one solution to this equation, and that would be if p and q were both equal to 0, making both sides equal to 1. And you can kind of see that if you have a bunch of 2's being multiplied together or divided, then that could never really equal a bunch of 5's being multiplied together or divided. So the only real solution is that p and q are both equal to 0. And since I assumed that q was not equal to 0 in the very beginning, then this is where my contradiction is. So I can therefore say that log base 2 of 5 is not rational, and in fact it is irrational. All right, so that's just one example of how that would work. Now we have the second type of proof. We're going to call this the Pigeonhole Principle. That's actually what it's called. And what it says is that if n plus 1 pigeons are placed in n pigeonholes, then there is a pigeonhole that contains at least 2 pigeons. And you can kind of imagine that to be true because once all n pigeonholes are filled, assuming that they were filled each with 1 pigeon, you've still got 1 pigeon left over. It's got to go somewhere, so it's going to have to go in a pigeonhole that already has a pigeon in it. So there's where you have a pigeonhole with at least 2 pigeons. Now the general pigeonhole principle says that if I have k times n plus 1 objects divided into n groups, some of which can be empty, then there is a group that contains at least k plus 1 objects, which makes sense. Even if you didn't have that plus 1, you could evenly divide the k objects into n groups, but now you have this plus 1 left over. It's got to go somewhere, so there's going to be a group that has at least k plus 1 objects in it. Okay, so that's the pigeonhole principle and the general pigeonhole principle. So for example, if I have 19 points drawn inside of a square of side 3 centimeters, we're going to use the pigeonhole principle to show that it's possible to find 3 points that form a triangle that has an area less than 1 square centimeter. So how would we do that? Well, I can divide each of the sides of the square into a centimeter, centimeter, centimeter. So that means I've got actually 9 squares. Each of them is 1 by 1 or 1 square centimeter. Now, if I wanted to be really conservative about this, remember I've got 19 points. So what I could do is I could put 2 of the points in each of those 9 squares, and that would be 18 points taken care of, but I've got 1 more, and that 1 more point has to go in a 1 by 1 square that already has 2 points in it. So that means there is going to be a 1 by 1 square that has 3 points in it, and I can make a triangle out of those 3 points, and that triangle is going to have an area that is less than 1 square centimeter, since it's already inside of a square that has an area of exactly 1 square centimeter. So that's it for this video. If you have any questions, let me know, and I will see you tomorrow.